Next up, we have Jon NORDBY from Soundsensing, who's going to discuss HVAC and building monitoring using anomaly detection. And Jon NORDBY is a machine learning engineer with 10 years of experience developing software and embedded systems and data processing of audio and images. And he has a bachelor's in electronics engineering and a master's in data science and a specialization in machine learning for audio and sensor data. And since 2019, he's the CTO of Soundsensing, a leading provider of IoT sensor systems using sound as the primary data source. And their systems use noise monitoring and condition monitoring of machinery. So, Jon, I will turn it over to you and take it away.
Thank you, Chris. So, hi everyone. We're presenting today a case study in applying predictive maintenance and anomaly detection to commercial buildings. And we will include our learnings from the last 3 years of testing and developing and deploying this use case in the market. Just to be on the same page about commercial buildings. So there are buildings that are primarily used for commercial purposes, for example, offices, hotels, restaurants, retail shops, and so on. However, the term sometimes is also applied to other non-residential or industrial buildings, such as schools and similar. So a commercial building is used by the tenant and their guests. And as users in the building, they have expectations that the building functions well, which includes typically a wide range of services, which may depend on the building type. But practically every building must provide at least clean air, heating, and cooling. And this is often referred under the term HVAC for heating, ventilation, and air conditioning. And behind the scenes, this requires various machinery. And there is a building operations team that is responsible for keeping it functional, which is a constant job to maintain the system because it's subject to mechanical wear and breakdown of electronics, etc. So most commercial buildings today rely mostly on manual inspections. A typical schedule for check-ins could be that every 1 to 2 weeks, members of the building operations team, they go in and do a quick check over the technical rooms. And then every 6 to 12 months, service technicians, which are usually specialists on particular equipment types, go in and do a full service or service checkup. In most cases, there are, especially in the weekly checkups, there's nothing to report, and it would be better to spend this time on more impactful activities for the tenants. And even with a strict adherence to such a schedule, issues do slip by and cause downtime. So manual inspections alone is a rather inefficient strategy for preventing incidents. And in many other industries, remote condition monitoring has become very established and nearly standard. For example, in energy production, in manufacturing, and process industry. And with condition monitoring, one continuously measures the health of the machinery. And the benefits of condition monitoring is that you have an improved ability to plan activities because you have some information about the health of your equipment. You have typically a reduction in unplanned downtime as well as faster recovery from downtime because you're more prepared. And the benefits of remote monitoring is that you spend less time on travel because you can access these things from your phone or laptop, and you can monitor a larger geographical area. And when coming to commercial buildings, we were doing dialogues and research with our customers to find out what is a good place to start applying this kind of technology and processes. And we found that the air handling system of ventilation, air handling unit, of ventilation systems is a very good place to start because all buildings need ventilation and there's a high impact on the tenant when the system doesn't work. The air gets bad very quickly, as well as a high energy cost if they are running when they should not or otherwise running incorrectly. And many of the maintenance issues regarding ventilation system is found in the air handling unit, which is a centralized component or centralized subsystem. So an air handling unit looks something like this. This is a modern type for balanced ventilation. It has 3 rotating components, an exhaust fan, a supply fan, and a rotating heat exchanger motor. And we are using vibration monitoring by having wireless sensors with MEMS accelerometers that are battery powered and transmit their data over Bluetooth Low Energy. They transmit the data to an IoT gateway, which then can communicate it to the cloud using 4G or Ethernet. And the sensors measure the vibration levels in X, Y, and Z, and they transmit both the mean vibration level as well as the peak vibration levels. And this is sampled for 1 second every 1 minute, which gives a rich source of data about these components. So in the industry, the accelerometers used cost in excess of $1,000 per measuring point. And they have documented performance tested over many years. However, this is too expensive to use in a commercial building because the consequence or the cost of a downtime is non-negligible, but it's not as large as a full production line that stops. So it needs to be cost-efficient system. So we have tested using MEMS accelerometer devices, and because we couldn't find great data on how well this performs under realistic conditions, we did our own tests. So we did tests both in the lab, where we could do destructive testing, and in the field, where we did stress tests of real systems up to the safe operating parameters of those systems. And we found that MEMS accelerometer sensors can detect a range of problematic conditions, such as shaft misalignment, bearing failures, unusually high loads, etc. And we realized quickly, and when we started, that what is considered normal for a machine varies very much depending on the particular machine. There are both variations based on the physical properties, such as equipment type, brand, and model, even when we're considering inside the problem space of air handling units, as well as the sensor placement and attachment method, which needs to be adapted to a particular device because they're not designed for mounting sensors on, as well as the existing equipment condition, which is often unknown. Before they start with condition monitoring, they don't necessarily know very well how things are going. There are also differences in how they operate. Some things are constantly on, some things have a weekly schedule, some things are based on sensors, like CO2 sensors from the room, and this gives much variation. So to handle this complexity, we use machine learning to automatically learn the patterns of a particular device using unsupervised anomaly detection. So in anomaly detection, we learn the normal pattern, and any change from that is considered anomalous. If it's a severe anomaly, meaning it has a high anomaly score and it persists for a longer period of time, typically more than 1 hour, so on, then we consider this as an alarm. And we have tested many approaches, and we're currently mostly using custom models based on the Kappa framework. And that is specifically designed to handle well with called collective anomalies, so longer periods of time in an anomalous state, which is indicative of a machine state change or condition change. And so here are some examples from the real world. This is production data. So here was a heat exchanger motor, which started to get erratic vibration levels around this red line in the center. And an alarm was raised, and the building manager was able to confirm that the motor was indeed failing. It hadn't stopped functioning yet, but it was very close to failing. And they were able to fix this before it completely failed, so there was no impact on the tenant. And interestingly, this incident happened just 1 week after the service technician had done a full service of the system, which highlights the importance of continuous condition monitoring. Here's another example where the vibration levels of a supply fan started to increase gradually and accelerating manner after having been flat for many months prior. And the service technician was sent after the alarm, and he confirmed that the bearing was failing and scheduled a replacement a few weeks after when the part was available. And this is a typical case of a bearing wear out, well known from literature and experience. And in a building, it's not a question of if you have this, it's a question of when and where, because you will have many of these over the years. And we also learned that, somewhat surprisingly, it's quite common in buildings that equipment is sometimes on when it should be off, or off when it should be on. And there are a wide range of sources, including configuration problems, software, and communication protocol issues. Here's an example of a system that was running day and night, so continuously, regardless of if anyone was there, and had been going on for several weeks unnoticed. And this was spotted during our installation. But of course, the system also automatically flags this if it would start to appear after a normal scheduled pattern, as you see on the end here. This system here is using a classic DSP architecture to extract vibration levels, which is already a very useful indicator of machine health, as the examples show. However, it's known from vibration monitoring literature that there are many more advanced ways of analyzing vibration data that can give an even better estimate of the machine health. So running tinyML models on device is key to doing this in an efficient way. And we have now started to test this out to, for example, estimate the rotation speed, the number of starts and stops, as well as changes in the frequency spectrum of the vibration signature. So to summarize, the benefits from condition monitoring that are well known from industry, we find it to transfer very well to ventilation in buildings. And we find that vibration monitoring with wireless MEMS sensors can effectively detect many common problems. And air handling units are a very valuable target for condition monitoring in buildings. And anomaly detection, we have found as a key technique for automatic detection of these kind of problems, and that it enables alarms with an early warning of failures with up to several weeks of alarm before a functional failure appears. So that's all I had. Thank you so much.
Yeah, thank you, Jon. That's a great presentation. And I think it's a good use case that highlights some of the things we talked about up front, which was the mix of approaches depending on the availability of data. So where you didn't have data that exists, you used unsupervised machine learning approaches and anomaly detection. And then for more characterized things like bearing faults, then you could rely on those types of models. So thanks for the specific use case and insights.